In translation, we have a fluid element, and for simplicity we have a two-dimensional Cartesian framework here, x and y coordinate, and where we have a fluid element which is shown here with the help of a point having dimension in x and y direction of size delta x and delta y. In this fluid region, a particle is moving, and we have u is constant and v is also constant. When u and v, where u and v are the velocity component in x and y direction. When u and v are constant, then this fluid particle having size delta x and delta y in x direction and y direction will translate and take these positions, point number 1 at time, say some time t is equal to 0, and this is point number 2 at some time t is equal to say 2 seconds, and this is point number 3 at time t is equal to say 3 seconds in fluid region. These dimensions delta and delta x, delta y will remain same, and the included angle between these two sides will remain 90 degree. This is called pure translation. Fluid is under pure translation. Now we may have another situation where in a fluid region u is function of x. U is function of x means u is varying in x direction, and v is function of y means v is varying in y direction. If u is varying in x direction, v is varying in y direction, then the fluid element which is A, B, C, D gets deformed and take this position A, B, C, D after time delta t. So this thing we discussed in the last class, and we found that we will have strain rate in x direction, which is designated by epsilon xx rate is equal to del u over del x, epsilon yy rate is equal to del u over del y. Now if we have u as function of xy and v as function of x and y, then what will happen? So we have a fluid element A, B, C, D in a two-dimensional Cartesian coordinate system, and if u and v both are variable in x direction as well as y direction, in that case what happens to this fluid particle having size A, B, C, D after time delta t? So as far as the linear deformation is concerned, means this AB will be subjected to linear strain, and that linear strain is equal to basically del u over del x in x direction and del v over del y in y direction. Now because of this velocity component varying in the y direction also, we will have the movement of v with reference to A in the direction which is 90 degree, right. So that's why we will have this angle. This angle is designated as delta v. Now how can we calculate this delta v? At this point in this direction we have velocity v only, and at this point in this direction we have velocity is equal to v plus del v over del x, del v over del x del v over del x multiplied by delta x, multiplied by delta x. So v plus del v over del x into delta x, this is the velocity difference. Because of this velocity difference, this particle B will travel at 90 degree, right. So in time delta t, what is the movement of this B with reference to this horizontal line? It will be v plus del v over del x, which is gradient in x direction, multiplied by delta x, this whole bracket multiplied by delta t, this multiplied by delta t. So this distance arrow is written here, this is del v over del x into delta x into delta t, right. Similarly, what will happen to point D? This point D will have linear deformation as well as angular deformation. This linear deformation will be equal to del v over del y, and angular deformation, which is measured with the help of, let's say with the help of this distance is equal to because this particle d will move in x direction because of the velocity in x direction. So velocity at a in x direction is equal to u, and velocity at d in x direction is equal to del u over del y multiplied by distance, distance is delta y, and multiplied by time. So by this distance, this particle d gets displaced in x direction and takes this position, and with the help of this horizontal distance we can find out this alpha, right. So del alpha and del beta can be calculated. How can we get this del beta? Del beta is equal to this perpendicular distance divided by the horizontal distance. What is del alpha? Del alpha is equal to this perpendicular distance, which is equal to del u over del y into delta y divided by delta t divided by this distance, which is equal to delta y. So with the help of this we can get the angular deformation, right. Del alpha over del beta plus del beta over del theta, right. At what rate we have angular deformation? So here we have angular deformation del alpha and del beta. How do we get del alpha? Del alpha is equal to this perpendicular distance del v over del x into delta x into delta t, and then horizontal distance. Horizontal distance is equal to delta x. Delta x was the original distance, 1 plus del u over del x into delta t. This we have understood in the last class, and we can still understand it, that what is the variation in the x direction of the fluid element having size delta x in x direction. So delta x plus some distance, because we have a differential velocity at point B, and what is the differential velocity of B with respect to A is equal to del u over del x, right. So because of this, in time delta t, this B particle will travel in x direction by magnitude of del u over del x into delta t. So what is the length in x direction is equal to delta x was the original plus addition of this. So if we have a limiting condition, because we have a point, so for point we have limit delta t tends to 0, this is tan inverse, this may be written as del v over del x into delta t. Similarly we have delta v. Delta v, we have a tan inverse, this distance travelled in y direction, del u over del y, this distance, this perpendicular distance, del u over del y into delta y divided by delta t divided by this distance of AF, right.